Welcome, everybody. This is a hybrid meeting. For those of you online, hi. If you look at the top left of your screen, you should see a small green shield. This symbol means that you are asking for the most up-to-date version of Zoom and that it is secure. Questions can be asked at the end of the lecture, but as you are muted, please use the chat facility. If you're online, use the chat facility to ask your questions, and then your question will be read out by Dr. Robert Massey, Deputy Director of the RAS, in the questions session. So please do answer questions online. We don't get that many questions online. We wonder if there's anybody actually out there. So either ask a question or send cash. I don't mind which one. Okay. Can I just remind you of an important deadline for the Society, which is Friday, the November 25th, which is the deadline to either propose a colleague or put yourself forward, that is allowed, for election to council the next session onwards. So deadline for election to council nominations, either yourself or a colleague, on Friday, the 25th of November. Before then, please. Well, passing on to the program today, I'm very pleased to welcome Dr. Olivia Jones, who's going to talk about early science with the JWST. Now, many of you, or some of you anyway, have been to the session today, the specialist meeting, which was chaired, in fact, by Olivia. And I must say, it was tremendously exciting, very well run as well, I've got to say quickly. Here. And I honestly, I just sat there enthralled at some of these new results, these pictures, spectra. I just talk about a golden age. It really is so exciting. God, I sound like a television presenter. I'm sorry. Didn't do that. Terribly exciting. But there was one quote though, which I must share with you. One of the, I can't remember who it was, but someone said, "The universe is amazing and beautiful." That was coming through these investigations. I think that's something when we do our public stuff, don't forget that. That's amazing. And for us too, the universe is an amazing and beautiful place. And here's a new way of looking at it. So I'm very pleased to introduce Olivia Jones. She's STFC Webb Fellow based at the Astronomy Centre in Royal Observatory, Edinburgh. She has a PhD from Jodrell Bank in astrophysics in 2013. Then worked at the Space Telescope Science Institute, home, of course, of the Hubble and JWST missions, prior to moving to Scotland. She's an expert in infrared astronomy, beginnings and ends of stellar evolutions, etc., etc. She's currently a member of the Webb instrument team and was involved in supporting its launch, commissioning, and the first observations earlier this year. So over to you, and wow us all, please.
Thank you very much for that introduction. It is a pleasure to talk to you about early science for JWST. I have half an hour. We spent the last full day discussing the last 5 months of observations with JWST, and there is a mountain of new science and rewriting the textbooks as we go. So this is going to be my own personal bias subset. I'm going to try and cover the main broad themes, but there is a lot of science out there. There has been at least 97 papers on the high redshift universe alone. That was a fact that came out to this meeting. I have not read 97 papers on just the high redshift universe, just to let you know. So it's an overview of the wonderful capabilities of JWST and some of the early highlights from my perspective. Other people in the meeting may have very different perspectives from earlier in the day. So I really like this comic talking about the best telescope and best camera. And I would have to agree with it that the best camera is definitely the one at L2 where JWST is. So I'm going to just briefly go over the mission, a bit of commissioning, and then selected science highlights from my perspective. So JWST has been in the news an awful lot, which is great. I really love the enthusiasm for the public and the scientific community for what Webb is doing. It is the biggest telescope launched into space with its deployable 6.5-meter mirror. And then this telescope-sized sun shield that's cooled the telescope down to working the infrared wavelengths. And that's optimized for spectroscopy, and seeing a whole new high resolution view in the infrared. It was launched on Christmas Day on an Ariane 5 rocket, and the launch was absolutely spectacularly perfect. We couldn't have done better. And due to the precision of the launch team, the mission of JWST, it says 10 years here. I think we're at least 20 years plus. Oh, okay. Right. So yes, so it was 5 years was the minimum, 10 years was the goal. We are in at least a 20+ year regime due to the perfection of the launch. And it's unclear what will be the limiting factor the JWST lifetime will be. So that means I think my entire career with Webb is nicely ahead of me, which is great, because I don't think it's going to stop producing science revolutions in the near future. Just to see where this compares in terms of other space telescopes, Webb operates in the near to mid-infrared. So there's some overlap with where the Hubble Space Telescope is. So the longest wavelengths of Hubble overlap with the shortest wavelengths of Webb. And then previously, one of the NASA's great observatories, Spitzer, which had an 80-centimeter mirror compared to the 6.5 of Webb, operated from 3.5 microns all the way to 160 microns, whereas Webb operates out to 28 microns. So there's an overlap with two of the great observatories from NASA. But that means there's a whole realm of discovery space at high resolution, which Webb produces. And so, yes, we did. Are you going to play? This is just the perfect launch. Christmas for me was quite a stressful day. I was not relaxed at all. Okay, well, we're not having the videos. So we did have a perfect launch, a flawless deployment, absolutely beautiful. This was it, moving away from the launch vehicle and the sun shield deploying, not the sun shield, sorry, the first stage of the unfolding process where you could see the solar panel deploying. And I was very happy by that point because it deployed slightly early, and that means I knew launch was a success. And then I went and enjoyed the rest of my Christmas day. Happy in the knowledge, a job well done by the launch team. Following launch, there was then 6 intensely busy months by the commissioning and instrument teams. And this has been a work by hundreds of people just to get the instruments ready for these beautiful pictures and spectra, which I'm going to show you later. So the first part of the after launch was the deployment, the traveling to L2, and the unfolding of the mirrors and the sun shield and the alignment, making sure everything was just fully deployed as expected. Then the cooling process needed to start. You can't really start cooling down the instruments until the sun shield was fully deployed. This was a very long process, and some of my colleagues, bless them, were spending Christmas and New Year watching very small changes in temperature happen for many, many months. Luckily, I was not, so that's part of the whole telescope commissioning, and there was 2 people on console for each instrument 24 hours a day during that time. That was a lot of people, and especially for Miri, just watching it cool down before any science observations had gone on. So thankfully, I didn't get to take part. I got to be at home not doing that, but many of our colleagues were very much involved in that commissioning, and that was when getting all the mirrors aligned. Then finally, 120 days after launch, the science instrument commissioning began. It's where we start to see those wonderful alignment images of the mirrors, making sure, and at this stage, when this first data came down, I think many of the commissioning teams just knew this is nailed it. We were in excess, it's going to go very well. And so through commissioning, this was a very exciting time when some of the early release observations were taken. I was on console operating the telescope during this time, and they were still top secret from me while I was on there while these observations were being taken. It was a very secretive process. So I didn't really know what observations were being taken until the image reveal day, even though I was working in mission control at that date, which was great, but a fun time. Just in case you are interested, this is what mission control looks like. At the back is the missions operation manager, or MOM, as we called them over the headsets. You can see a timeline of universal time, all the different screens and instrument alignments. This is where most of the people who were commanding the telescope were based. And on the other side of that glass wall was where the science instruments were. So I had a window view over the forest. This is at Space Telescope in Baltimore. And so we communicated a lot via headsets. But this is what missions operation looked like most of the time, 24 hours a day for those 6 months. It was a very intensive period, but wonderful, hard work, and just well-oiled machine put together. And this, oh, I'm glad this works. We are seeing a revolutionary change in capability. This is the mid-infrared instrument. And This showed you what we had before, which was the WISE wide field camera in the infrared as the patch of sky in the magellanic clouds. And this was the very first data I saw from MIRI, which is the team I'm a member of. And you can see the change in resolution of stars. And not just the change in resolution on the stars, but you can see then these structures, these wispy structures in the interstellar medium called PAHs. And yes, I think at that stage, our Slack channel lit up of commissioning, and we knew we were in for a very good time of science for the next decade and beyond. So that was the mid-infrared. This is one of my own personal programs, a proprietary. You are the first people in the world to see this. Please don't show anyone else. This is my PhD student, Connor Nally, who's working on this. This is a galaxy that is 0.5 megaparsec away. So this is a very long way away. And before this is the Spitzer data we had for this galaxy, where you can see a few of the brightest stars. But I think you can see this long diagonal streak. Look how many stars that changes into. We are really changing the field of stellar populations. This makes it quite challenging for our data analysis, just to see how many stars there are in these fields. But yes, we are starting to, so this is halfway the distance to Andromeda, this galaxy, to put this in context for those of you observing the night sky. And we are seeing stars to very faint magnitudes, or at least in the 26, 27, 28 magnitude regime. Just for the astronomers who know those numbers, the changing capabilities is astounding. And then it's not just imaging, there's the vast array of spectra you have. And I really liked early on today learning about Peter Jacobson, who actually put together quickly the template to observe these 200 spectra in the galactic center, just a field. And just, this is a very dense field. This is all the shutters open. And in one go, you can open up these very tiny micro shutters and just obtain from 1 to 5 microns, 200 spectra of objects. And I think that capability is great. It's going to be wonderful for globular clusters, star formation regions, galaxy clusters. So these are some of the very exciting, apart from my program, commissioning data that just made me go, wow, we are in a complete revolution change in terms of astronomy in the infrared. So that was the quick highlights of the mission and commissioning, but I'm really here, my remit was to talk about science with Webb. And so with Webb, we can observe from solar systems to the very first galaxies. In fact, one of the targets down the bottom there is supernova 1987A. Keep an eye out for that. That's one of my programs. I'm not showing it today, but do look out. Hopefully the BBC will show it in the future. I think there's some very beautiful data there. But we've seen the Horsehead Nebula. It's just a very great time for astronomy, from very close by to extrasolar planets to this very early universe. And why is this so great? And it's because the instruments are optimized for this type of observation. There's a very big, bright infrared universe. So there's 3 instruments that operate from 1 to 5 microns. So these are looking for the cooler red stars, looking at galaxies. You can see through dust. You can see stars in the very early stages of formation. And then MIRI, which is the longer wavelength instrument, which is the one that needs to be specially cooled. It's 7 degrees Kelvin, whereas the rest are just passively cooled by the sun shield. And MIRI operates from 5 to 28 microns, and it's aimed for planets, comets, asteroids with the warm dust, but by warm, it's pretty cold dust in the grand scheme of things, and protoplanetary disks. And these two types of observations and these instruments complement each other to give us a revolutionary view of the universe. And this covers the 4 main science themes. And I'm going to try and show some highlights of each one of these sections in the remainder of the talk. And so we really want to go from the very first light. Hopefully we will see that let there be light moment in the universe when we're trying to look with Webb for the end of the dark ages and the first light in the ionization. Coming a bit closer in, want to see the assembly and evolution of galaxies. Where do all the metals come from? You know that famous phrase, we're all made from stardust. Well, it may not be all stardust, it may be colliding neutron stars or a few other exotic events, but these are all the chemical evolution of the universe is happening. The galaxies are merging and smashing into each other and interacting. And there's a low change in the system. So what you see today from our own Milky Way to the galaxies in the very early universe, where do they get that mass and structure? Coming in a bit more closer to home, you want to look at stars and protoplanets. So how do stars form? How do some of the early stars in the universe form? How do massive stars form? These are all actually quite unanswered questions, and forming these very first planets as well in the disks around stars are all questions that Webb is hoping to answer. And then The closest to us of all these four themes is planets and the origins of life. And Webb is not just good for detecting extrasolar planets and looking at the atmospheres of these more distant systems, but it also actually, surprising to me, has given us a whole new view of planets in our own solar system. So there's a beautiful image of Jupiter with the aurora, and I was blown away by that. The dynamic range of Webb from these very bright solar system objects all the way to this very first light is just astounding that one telescope can cover this entire range. And so this is what we're seeing. A lot of work with Webb is to look further and further away to galaxies and stars that we've not seen before. And so this is the evolution of the universe in a dynamic system with Webb, us at the present, with all these wonderful spiral galaxies, all the way looking back from the first galaxies. You can see the change in shape to the reionization era, where there's no galaxies, the radiation era, and the Big Bang. And what happens is the amount of star formation changes throughout the universe. And so if you look at galaxies a little bit further away with conditions similar to cosmic noon, where most of the star formation happened, you can then start to infer further back to the more distant galaxies. And that's what my own personal science is involved, is looking at nearby galaxies and individual stars in them to look back to the earlier extrapolation to the earlier universe. But also there's stellar mass. You get the assembly of galaxies as time passes, as you come closer to us. And then finally, the chemical enrichment. I told you, the universe becomes more metal rich. And again, I'm an astronomer, so that means anything that's not hydrogen or helium, it is metals in this system. This changes as the universe evolves. And this is a good picture, so Webb can change, observe these different components, and then that will inform chemical models and stellar evolution models and galaxy models. So then go back to these very first stars in the universe and first galaxies. And a lot of Cycle 1 programs are covering that sort of redshift of 2 to, I think at the moment today, it seemed to me the most reliable redshift galaxy was around a redshift of 17. So I think that's quite a way push back time to the very earliest universe. And I'm sure we're going to go much deeper. This is some of the very provisional early results, a redshift of 17 of a galaxy. And a lot of the results have been these stunning deep field observations that aren't even that deep. This is just a very small fraction of the time compared to even what the Hubble Ultra Deep Field was. So on the left here is showing the MIRI image. So that's the mid-infrared telescope. So anything red in there is either a very, very long way away or it's very dusty. And as you can see, there's lots of very red galaxies. And then on to the right figure is the NIRCam image. And I think you can see this is a lensed system, but there's just look how many galaxies are there. I think you can't really observe Webb apart from in a few very dense stellar fields without seeing galaxies everywhere. There's some wonderful shapes. I have to say I've quite enjoyed looking through Webb data and just naming various galaxies. I'm just thinking, oh, this is a new one, this is a new one. And I can lose quite a few hours of my time when I should be doing science, but I'm just looking at new galaxies. That isn't my science program, and it's beautiful. But through this data, this is where some of the candidate very high redshift galaxies have been seen. And what you want to really look out for in these images are ones that are very bright in MIRI, very red in MIRI, but may not even be present in all the filters in NIRCam. But I think this is a very stunning, very first image released from Webb. And a very key component in this is the O3 emission line. So it's not just the imaging, it's the spectroscopy that goes with it. And so with the spectroscopy, and we heard a lot of talks earlier on in our discussion meeting today about the O3 line. This absolutely astounded many astronomers that this line was detected. And it really does change the field, because with this O3 line and other oxygen lines, you can take the ratio of them to determine the abundances to a very high degree of precision. You know, the abundances, you can learn the temperatures, you can better tune your models, and you can learn a lot more about the physics of these very early universe galaxies. This had not been really accessible from any other telescope before. And this was very hard to do with Hubble. It's been done with Hubble, maybe not this line, but this technique has been done with Hubble. But to be able to do this so easily in the very first just provisional images from Webb and spectra, I think is outstanding. There's going to be a lot of progress made in this. And this really actually lets you determine how much metals are there. And these, looking back in these galaxies, the one of these really 3 high redshift galaxies seem to have a very low metal abundance. And they're the ones that the astronomers are really looking out for, these very distant galaxies with very low metal abundances, the earlier universe. the very first light. So I think that's a very exciting time for the high redshift universe community. Coming a bit closer to home into the assembly of galaxies, this is a wonderful picture of this Stephan's quintet, I think is the correct one of these colliding 5 galaxy systems that are interacting. One of them is actually not colliding, it's just a superposition. But this is the Hubble image of this beautiful system. And then this is the MIRI image. And I love this. I think this is gorgeous. So this blue galaxy is the one is a bit closer than the rest of them, the more distant. But in that galaxy, which is at 13 megaparsecs away, you can see individual stars and star formation regions. So for me, in my own personal science, that's very exciting, how far away you can resolve individual stars. But to most people looking at this image, what they're really excited by is all these galaxies interacting. Can you see this green component across the field? That is your PAHs, your polycyclic aromatic hydrocarbons, or your burnt toast, or your car exhaust. And you can see that being dragged across, as the galaxies interact, that material is being pulled across into the intergalactic medium between these galaxies. And you can see that info, which you can't see at all in the Hubble images. And so this is what I mean by a whole new universe. The top galaxy, that's sort of one that's spectacular, has a very much the PSF profile. It actually has a black hole in the middle, and that has both imaging and spectroscopy. And you can from that determine the abundances of material falling into the black hole and the AGN in the center of that galaxy as well. This is a very powerful image, and I absolutely adore it. Not only does it look stunning, but the amount of science that each of these images contain is spectacular. And this is just a small number of hours. And so it may be potentially that I was on shift during one of these images being taken. I just will never know which ones they were. So I guess that'll be a mystery for everyone in my life. So maybe I was on console while this one was being taken, but who knows? But this is what I mean. You have the spectra as well. And I think that combination of imaging and spectroscopy is really where Webb's power is. And so this is that, again, in the left image, then is the NIRCam image. They've zoomed right into the center of the galaxy black hole, the AGN. And then you can really see all the iron and argon lines and sulfur lines. And then as a dust physicist, an astrophysicist, I was really excited that you could see the silicates and this absorption, which is very small, sort of sandy particles around a black hole at such distances. I think this is stunning. So now I'm just going to come to the other end of the scale, looking at exosolar planets. And so one of the ways to do this is to look at transits. So where you observe a star, you see the planet go in front of the star, and then you keep observing and you see the planet go behind the star. And by the starlight then is blocked by the planet, so you can see if there's how many planets are there. You can work out various properties of the system and the orbital parameters. And not only that, if you're just doing images, you can use that to detect exoplanets, but you can also use this technique to determine the spectroscopy and the chemical composition of planets in this technique as well, if you're using various different modes. And so this is very powerful. So you can work out the atmospheric composition now using this technique for a much larger parameter space. This planet has been looked at before up until about I think it goes to about 1.5 microns with ground-based instruments and with Hubble, but Webb really pushes this out. So you can then see this water vapor. And I think if I remember correctly, that this is like extremely, extremely hot, very much clouds of H2O around this hot gas giant. And the fact we can now start to a very high degree of certainty, look at those error bars, I think it's beautiful, really see about the chemical compositions of these different planets is, again, a very exciting time for exoplanets, and not just pushing, oh, we've detected them, which I think is from 1995 to we now have thousands of exoplanets, but we can really characterize the composition of their atmospheres. And this was one of the very first transits that Webb took with MIRI. And I was on console for this. So this was during the commissioning period. This is a 5-hour observation of the super Earth. I'm not saying its name. And so the day before, when we knew this transit was going to happen, we had a very finite window to make sure we targeted this transit exactly. So some of my colleagues were in the room making sure, right, we need to make sure the observations start beforehand. We don't want other observations to overrun. This needs to happen exactly at the right time to make sure we start at the beginning and end of the transit. So the day before, we made sure that we had a talk with all the schedulers in that room I showed you earlier to make sure that this was in the schedule correctly and nothing was going to mess with these observations. Then it happened to be the next day, I was on console again and these observations were taken and we were frantically refreshing the archive to see, has the data come down yet from Webb? It had done. And then experts on Super Earth and the calibration commission downloaded the data and you could see it. I think you can see here the orbital phase. So that's time across. This is the white light. This is all the wavelengths together. And you can really see, okay, it helps when the green is where the transit is. You can, and I do mean it, if you get your computer, you come to this computer, you can see there is a dip even just in the raw data. But when you do a bit more processing and calibration, and you can really see where the transit happened. And I think that was a very good day for our calibration team. I think this is a very exciting observation. So this is the first transiting exoplanet taken with MIRI. And I get to be on console during it. I didn't have much part in this observation. I just got to see it happen in progress and see my colleagues very happy that this was working when we tested this mode. And I think just it shows the power of Webb. Again, this is just a different observing mode to what we saw before. And then we can do not just taking the spectra, you can see the first direct infrared images of exoplanets. So this is work by Aaron Carter in 2022. Well, everything is in 2022, right? We're in the first year of Webb. Looking at the exoplanet, again, another long number. And what you can see here is the star surrounding it, and then the NIRCam and MIRI observations. This was taken using a coronagraph. And what you need to do with this is to block out the light of the central star using the chronographic modes. And then you subtract any residual light. So you can really then just see the exoplanet once you take away all the starlight. And I think this is great that now in the mid-infrared or in the near and mid-infrared, across multiple wavelengths, you can directly image exoplanets and see this structure and how much heat there. I think this is just awesome. So this is a new, I would say this is one of the very early highlights. To be fair, they're all highlights. It's just for all fields and of astronomy, it has been a revolution in what we can do. And then now coming a bit closer to the science that I'm personally interested in, star formation, the beginning and ends of stellar evolution and chemical evolution in the galaxies. I think I have been very excited to see what the pillars of creation will look like with both NIRCam and MIRI. I knew these observations were on the cards at some point, and I've been really waiting to see. I've got data nowhere near as pretty as this, but hopefully the Space Telescope team will get onto it when I make a nice press release. But to see star formation like this is astounding. It really is. Going to the mid-infrared and then near infrared and then the mid-infrared is really like peeling back the layers of an onion that what you can see with Hubble. So the Hubble image is on the left. I think you can really see these really red stars. They are the stars that are in the very earliest stages of formation. And I really wanted to see what they look like with Webb. I really did. And so the universe granted us that, the public engagement team did. The middle image is the NIRCam data. And again, look at these. Even as you go to longer wavelengths, you can peel back more things. You can see into the heart of the dust. So you can see the structure changes. You can see some stars that were red previously and now just look like normal stars. You can see the vast array of stars in these images as well, just across the field. But really, what really lit up to me is if you look at the very top of these pillars, especially the middle one and the smaller one, just how red they are. And that means you know that stars are being created and being born right at these edges, these pillars in these very dense dust structures. And I couldn't wait to see what then. NIRCam got released first. And I was like, right, MIRI is going to be even more amazing because we can peel back more dust. Wow, what do we see with MIRI? It's not what I expected at all, but equally stunning. This is observing, I think, in 7 microns, 15 microns, I think 21, but please don't quote me on that. It's more designed to look at the PAHs. So what you're seeing here, this green, is this PAH emission. Again, that burnt toast, those silicon, but really like how much it's all this star formation region is just dense, and it's so dense. I was expecting we'll be seeing right into the heart of the star formation, and you can see at the top of one of these pillars, individual, still very red stars. So you know that these are in the earlier stages. I think in that middle pillar, if you look carefully, oh, you can look very carefully. There are two stars there that are still very bright red, and you know that they are really, really young. Just the fact that they are in the stem structure. But the fact that you still can't see all the way into the heart of this just shows you how much dust is in these pillars. And that amazed me, because I thought with Webb, especially given how sensitive it is and what it's doing previously, I think that really shows just the outstanding, just how much dust are in this star formation region. And again, if you look to the main pillar, the biggest pillar, you can see at the tips just where all those really red sites of star formation are, just these one stars, like the one or two really red things. And I think it's just a very beautiful image, and the science it contains is outstanding. And so, yes, I was very much looking forward to this, and I hope you can tell. Anyway, moving on. So those red stars, what do they look like? Before I mentioned there's been at least 97 papers produced on stars in the high redshift universe since launch. For protostars, there's been one, and this is the one paper that shows what these images look like. So this is a spectra. So think of those really, really red stars in those images. This is a typical spectra of what one of those stars would look like. So this was taken with the MIRI MRS. This is the 5 to 8 micron spectra. And what you can see here, I've seen many images over the years of what this will look like with Webb. And when this was produced, I was so excited to see these results. You can really see the ices. So you have H2 ice, you have all these not emission features, but they're in absorption. So where you can see that dashed line is where you'd expect a baseline to be. For lots of the high redshift universe, you work in emission, so things above that line. But for these very embedded cool objects, you're seeing things in absorption, and that makes the analysis a lot more complicated, and that's why you don't see as many papers so far yet. But I love that you can see things like methane, CH4, NH2, just all these wonderful, beautiful chemicals. And I think you can really see these dips in the spectrum really clearly. And this high resolution mode will let us learn a lot about how stars are formed, especially these protostars that are in the most embedded phase before they even start to ionize their surroundings. So you won't be able to see this at all in the Hubble wavelengths. It's only in fact, even in near-cam wavelengths, you are not really seeing these objects. It's when you get to the mid-infrared MIRI wavelengths where these deeply embedded objects really light up, and the chemistry involved. And then it's out of this material what your planets and disks will form out of. So it's very key to understand the chemistry in these regions. So I was very excited to see this, but it's quite a complex process to do, so you won't see quick results along this manner. So then to the other end of chemical evolution is dying stars, so Planitia Nebula. These are stars like our sun that have finished off the main sequence, turned off, and then have turned into Planitia Nebula. And one of the most beautiful sets of data is this commissioning data from the Cat-sized nebula. Again, I'm biased, I think, probably a bit towards MIRI and spectra, but this is beautiful. So we have the imaging of the Cat-sized nebula at 5 microns, which is the left image, and then you can see the various squares where we got spectroscopic data. What you can see with this is the 3D structure starts to appear. So you can isolate individual lines, and we don't just have lines in a spectra, we resolve these objects. So you have the spatial information as well. So with the spatial information and where the lines are and the line widths, you can start to build a 3D picture of what these beautiful, stunning Planitia Nebula look like. And I love this sort of crisscross pattern you can see in the neon line. It's very different to what you see in just the combined image at 5.6 microns. And I think there is a paper submitted by a lot of the Planitia Nebula community on this particular object. So I've not seen that yet, but I'm looking forward to that highlight when that is published. Keep an eye out for it all. I expect it will be stunning. And then finally, this is one of the programs that I've been involved in, is looking at the massive Wolf-Rayet star, WR140. And so previously, this is unlike our own sun, this is a star that was at least 10 times the mass of the sun. And it has a binary companion of another massive star. So it's two massive stars, one at the end of its life, one of them still in the main sequence, interacting. And previously, our best observation of WR140 was this image from 2009, where we could see the star and we could see this shell surrounding it. this is where it gets very exciting for me. This is what we see with Webb. You see at least 19 dust, no, at least 17. We decided 17 was the minimum number of dust shells. Please, you never want to be in a telecon of astronomers counting rings. But there's at least 17, probably 20. And each one of these rings is produced every 8 years, and it's like clockwork. It's absolutely beautiful, just this system. And the reason how this works is, okay, please play. Yes. Aha. Right. So we have the Wolf-Rayet star. This is the big star in the small orbit. And then you have this other massive star orbiting. And every 8 years when they interact, the winds, let's show this video again. The winds collide, the material is pushed together, and dust can condense. And so there's 130 years of stellar dust mass loss in each one of these rings. So we have both imaging and spectroscopy of this. So we not only know that there's lots of dust there, we know it's stable, and just the extent of these rings as well. It's 10 trillion kilometers, which is at least 4 times the size of our solar system. Just to put that in your head of how far away and how big this system is. And what we know is each one of these rings are made out of PAHs. They seem to be so common in any Webb imaging and spectroscopy as PAHs that seem to be across the universe. And so very tiny particles. And this actually has quite a lot of implications for the early universe, because how much dust and material is produced there is probably likely due to massive stars and supernovae, and because stars like our own sun can't evolve on fast timescales. And the fact that they can survive for at least 130 years in such chaotic and energetic environments really does bode well for survival in the interstellar medium for other galaxies. And not only do we have these images, at a similar time submitted independently, well, okay, there's a couple of 2 co-authors in common, was a model of actually how this works. So unbeknown to us, so the model was made, I think, before the observations were taken. And just look at that. That's where theory and science observations coincide, I think, to perfection. I think you agree that is rather spectacular, just how much it matches up throughout the orbital period. So it took, we got this data, I think with 18 hours later, it was over social media because it's part of an ERS program led by Ryan Lau, but amateur astronomers and the public were looking through the archive and just saw this and started making stunning images. I think there was a few articles in the press before then, but we'd already had a paper submitted, but we were keeping quiet about the results until that was accepted and gone through the refereeing process. But it was a very exciting time, and it made some interesting headlines along the way. It definitely wasn't aliens. We had the model to show it was all about the dust, radiation pressure, and drag that created these structures. So anyway, just to summarize, so far, it's been a great 5-6 months at least. It's wonderful. And just the dynamic range of Webb, we detected the faintest galaxies at the furthest redshift and observed targets as bright as Jupiter. We can obtain spectra of thousands of stars in a really dense field simultaneously. We can get IFU spectra, so resolve the imaging and spectra to an unprecedented level. The precision of Webb as well. So we can capture transiting exoplanets with superb precision. So I think this really bodes well, and just tracking your various objects. It's amazing, the engineering involved, not just the scientists, but the engineering and the teams of thousands of people have done a fantastic job. And there's been at least 100 published papers since July. I think it really is a real scientific discovery. So I just want to end there. These are the MIRI team and part of commissioning. This is me after a night shift as well, part of this. But thank you to all the many, many thousands of people, well, at least 20,000 people written here throughout the world who made Webb the success it is. Thank you, everyone.
Thank you very much. Questions, please. Yeah.
It's the redshift determined? Do you get a spectra that you can identify, or is it a more general process?
So this is not my area of science, but from what they do is they get many different wavelengths of imaging data. And what you do is look for the Lyman alpha break. So suddenly the galaxy will not be, it won't be visible in any of the shorter wavelengths. Then eventually at one wavelength, it'll just start to become very bright. The longer the wavelength that gives you a quick idea of how far away an object is. You can then use that data to then start to model with template spectra exactly how bright these are in the future wavelengths. And then by using the model and using some priors and Bayesian analysis, you can get an idea of the redshift and the properties. But do they agree with each other is still a matter, and it really does depend on calibration and systematics. This current early surveys didn't find the same targets, but this one Z equals 17 seems to be people agree on that one.
Possibly.
Oh, well.
A couple of questions online.
Yeah, we have, yeah. Oh, okay, great. Thank you. You've got 3 online, probably more to follow. And I'm also advised you have quite a lot of time for Q&A, but I'm looking at the chair will probably be right on that. But okay, so the first one is from Ian Robson. I'll read it verbatim. He says, brilliant stuff, 2 exclamation marks. Do you know who was responsible for selecting the color palette for the images, especially the galactic ones, to make them so beautiful?
They are a very awesome team at Space Telescope. There is a team, I think, of at least 3. There's videos online of watching them, how they select the color palette and involved. And it is to just bring out the different features. They tend to work on the idea that the shortest wavelength is to the blue and the longest wavelength is to the red. So they keep that genuinely in mind, but the color palette of how they exactly pick each filter is their skill. I've observed my targets come in the same wavelengths, the star forming regions. I can't even get close. And I know they could, but I have tried. It's a wonderful, highly precision, great way of communicating to the public the science.
Next one.
Brilliant. Okay. The next one is from John R. Hughes, and he says he's interested in some brief comments from you about how the international teams agree access time and prioritize what to investigate with so much to analyze. Is maybe off topic, but just wants a brief answer.
Well, it probably coming on to topic soon. Soon the James Webb Cycle 2 call will be out. Wow, yeah, that's coming around faster than I'd like. So you put forward a proposal to observe targets. It's based on the scientific merit of what you want to do. Anyone in the world can put forward a target and a scientific justification for that. Then panels of experts from around the world in each field rank those proposals and then allocate time based on peer review of how good and how much resources you think it will take. So it's a long process. It's very competitive, but I think it brings out the best science.
Shall we take one from the room and then I'll come back to the online?
Okay.
At the back there.
My question too is about the color palette. You know the wavelength of the light when it's received here. You also know the Z factor, the Z shift. Would it not be possible to reproduce the wavelength as it was emitted? Of course, any image, you'd have to reduce it to just the visible spectrum emitted to make it meaningful to the eye. But could that be done, and would it be worthwhile?
No, it wouldn't be worthwhile, and why would you do it? These things emit in the infrared. They don't emit at visible wavelengths, so it's meaningless to try and bring them to your eye. They're spectacular in the infrared. Leave them there.
Okay, fine. So it's not that a lot of the infrared is originally visible. That's what was in my mind.
No, they are bright in the infrared. That's where they look spectacular. It's not the optical where they're spectacular. It's the infrared.
Another one from online, please.
Okay, Stuart Eves is asking, to what extent does JWST evidence of galaxy structures in the very early universe call into question the current Big Bang model?
Pass.
Succinctly done there.
I think the short answer is it doesn't yet.
We're in the early days. I'm not going to comment further.
One here.
Wonderful talk, by the way. I wanted to ask, Is there a concern over the lifetime of JWST when we're concerned with space debris? We've already had one minor strike on the mirrors. I'm just wondering if it's an actual concern.
No, it's not a concern. We knew micrometeor strikes were going to happen. They've been modelled along the way. It will be a limiting factor at some point, probably for the coronagraphs first, but no, it's not a concern. Degradation is built into all the models and performance estimates.
I hope this isn't one of those, no, there's no hurricane. I'm presuming that the nominal thing is that predicted is okay, but keep your fingers crossed. Okay. Any more questions? One over here. Wait for the microphone, please.
How far away would the Sun and Jupiter have to be that you could resolve Jupiter with MIRI?
You can, well, we've observed, I think we've observed with MIRI, we've definitely observed with some of the other instruments, the structures and the aurora on Jupiter. So,
No. I mean, if the Sun and Jupiter were an exoplanet system, exactly that Sun, exactly that Jupiter at exactly that distance apart, how far away could that system be and you could still resolve Jupiter from the Sun?
I'm sorry, I'm not an exoplanet person. They're not calculations I would know off the top of my head.
Can you? Yeah.
Anybody like to? Anybody done the calculation in their head? John, you've done it. No. I'm from what I heard this morning. Have you got an answer?
There you go. I think there's an answer being
right. From what I heard this morning, the answer is it's not very good for doing that, but it's good for doing Jupiter's further out.
So 20 parsecs was the answer from Matt.
Yeah, and 20 parsecs, that sounds fair.
Depending on two things, depending on the resolution, angular resolution, but it's also dependent on how clean the image.
Yeah. Okay. Next question, please. John, did you want one? John Zarnecki at the back.
This is a comment rather than a question, and it's prompted by your last slide where you talk about people making JWST. And I'm reminded of Helen Walker, who was a fellow of this society for many years. And if I remember correctly, she was the test team leader for MIRI and spent many, many months leading the team testing and calibrating MIRI. And she spoke, I think, on the subject to the society. And it's a bittersweet occasion, really, because she died 4 years ago. So she never saw the results of all her labors. So it's good to remember all the work that she did, I think.
Thank you, John. Anything else online? Any more questions? What do you think? Yeah, gosh. Right, okay. Just while you're thinking of one more question, I was rather amused today to hear people saying, you know, I'm looking at this redshift 7 galaxy and this damn Z2 galaxy is in the way. You know, I wish they wouldn't have all these galaxies at redshift 2 that get in the way. And it reminded me of Messier and his, you know, Messier drew up his list of these annoying nebulae and galaxies that got in the way of discovering comets, damn it. So it's a nice historic parallel, I think. Any more questions yet? Before we thank again. Okay, I think that's it. Thank you very much indeed. Now we move on to a set piece lecture, which I've been very much looking forward to, the James Dungy lecture. Jim Dungy was a space scientist, I guess you'd call him, was involved in plasma physics, died in 2015, known particularly for his work on magnetic reconnection, and the James Dungy lecture is given annually on the suitable topic in geophysics, including solar physics, solar terrestrial physics, or planetary sciences. And this year, I'm delighted that Dr. Lucia Ray, I'm I knew I'd get that wrong, but not too bad. Lucia is giving the lecture from neither here nor there. I want to get this up on the screen. Do you want to do that while I'm waffling on? Okay. Lucia Ray is senior lecturer in space and planetary physics at Lancaster University. Her research explores the coupling of planetary atmospheres to their surroundings. In particular, she's interested in the structure of high latitude regions of the magnetosphere and how the planetary atmospheres exert control over magnetosphere ionospheric thermospheric cooling. I think I got that right, just about. So it's a great pleasure to welcome this year's James Dungy lecture.
All right, thank you for the introduction. So yes, I'm going to talk about the coupling between planets and their surroundings today. And the reason why I say neither here nor there is because you can't really talk about anything involving the coupling without really understanding the atmosphere or really understanding the surrounding environment or really understanding the in-between, which sometimes people classify as an upper atmosphere, sometimes people classify that as a high latitude magnetosphere. And we can talk about that a bit in our talk. So first of all, I know this is very much a mixed audience. So before I go into a lot of nitty-gritty details, what evidence do we have for the coupling of giant planets with their surroundings? Well, the most obvious evidence, perhaps, is the aurora. So we have aurora at Earth, and that is a signature of how the solar wind couples with our magnetosphere, depositing particles in the tail through reconnection, which are then channeled into the upper atmosphere and generating bright auroral emissions. At Jupiter, and this talk, I should say, focuses mostly on Jupiter, and I might make some references to Saturn and other systems. But at Jupiter, we also have aurora, and that aurora at Jupiter is seen in the UV, in the infrared, in the X-ray, and there are some visible ones, and we'll get into what generates that in a little bit. We also have perhaps the first indication that there was coupling between Jupiter and its surroundings in radio emissions. So in 1955, there was a radio source in the night sky. It wasn't very, very far away. It was more local to that. It was decametric radiation, radio emission associated with the moon Io as it orbits around Jupiter and travels through a plasma torus that we'll talk about in a little bit as well. We have measurements from many space missions, equatorial missions, in particular like Galileo, which give us indications that the plasma flow through these magnetospheres, so the material surrounding them, is not moving at the speed that we think it should. If all other things were being equal. So it's not moving in a Keplerian way. So that's telling us that there's something coupling that to another source of angular momentum. And we have measurements of the atmosphere. So the atmosphere of the giant planets is much, much hotter than it should be. If it were heated by solar radiation alone, it would be around 200 Kelvin. Instead, we observe temperatures of 800, 900 Kelvin. So that's telling us that there's a source of energy somewhere from outside that is heating up these atmospheres. And so again, the planet cannot be treated in isolation. And then last but not least on this figure, we have some images, direct measurements of particles in the in-between region from Juno. And so that is telling us that there are particles precipitating directly into the atmosphere in a way that we can infer from the aurora, but now we're able to directly measure. So what I want to discuss in this talk today is what are the respective roles of the atmosphere and the magnetosphere in generating all of the behaviors here. Now, the first thing I'll do is now properly introduce Jupiter. Hopefully everybody in the room is familiar with Jupiter. It's the king of the planets. It's the big one. It's the fifth rock from the sun, except it's not really a rock. It's the fifth gas ball from the sun, but that wouldn't have made a good sitcom name for all of you who watched bad 90s sitcoms, which is maybe one laughter in the audience. So one person. All right. So Jupiter has 80 moons, which is more than enough to keep track of. It's the largest planet, and one Jovian radii is roughly 10 Earth radii. Its atmospheric composition is primarily hydrogen, helium. There are hydrocarbons, and it's those hydrocarbons that we can see in the cloud structure. The ionosphere, so the ionized portion of the upper atmosphere, is predominantly H+ and H3+, although there, of course, are ionized hydrocarbons in there as well. It's a rapid rotator, so we're used to our measly 24-hour rotation rate on Earth. It allows us a nice time to sleep in the evening before we need blackout blinds, depending on what time of year you're talking about. Well, at Jupiter, you'd be a little bit stuck. It's a 9-hour and 55-minute rotation period. And it has a very, very strong magnetic field. The magnetic field is an offset tilted dipole to first approximation, but near the surface, there are much higher order moments, which are twisty and give us some particularly fun behavior to pick out of especially the northern auroral emission. So this is just a nice artist's image where they put a picture of Earth or an image of Earth on top of Jupiter, and it fits nicely inside the great red spot. So we're talking about quite a giant beast. Now, this massive magnetic field generates the largest magnetosphere in the solar system. A magnetosphere is the cavity carved out around a planet in space. It's carved out by the planet's magnetic field. And inside of that magnetosphere, the dynamics are largely going to be dictated by the magnetic field itself or by other factors internal. At Earth, our magnetosphere is largely empty. You can balance the magnetic pressure of Earth's magnetic field with the ram pressure of the solar winds, the material streaming off the sun. And what you find is that the boundary along the Earth-Sun line sits at 10 Earth radii. And it's a nice back of the envelope calculation that you can give to any undergraduate and they'll do it. And the nice thing is you can then say, so now go and look at spacecraft data. And what you'll find from spacecraft data is, oh, the magnetopause, that boundary sits at around 10 RE. Perfect. Builds confidence. Students happy. You're happy. Perfect. You wouldn't be able to do that at Jupiter. They could do that back of the envelope calculation. They could use Jupiter's magnetic field. They could use the solar wind ram pressure. And the value that they would find from that would be around 40 RJ, give or take. When we fly through this boundary with spacecraft, what we find is that the magnetopause standoff boundary sits between 63 and 92 planetary radii. That's quite a bit different. And it's telling us that there's something else that is balancing the pressure of the solar wind, and that's coming from inside the system. What that is, in the case of Jupiter, is an internal plasma source from the moon Io. And I'll talk a little bit more about that in a little bit. But the result of it in terms of the magnetosphere is that the magnetosphere is this vast thing in space. The standoff distance here is bimodal, depending on how the pressure is varying on the inside and how the solar wind pressure is varying on the outside. And you do have a population of plasma that is spun out into a disk. If you could somehow light up Jupiter's magnetosphere, you would find that it is the largest object in the night sky. So here, everybody in the room, I'm sure at some point has been somewhere, maybe not in the UK, at least not in summer or not during the rainy season or, well, that covers a lot of it. And you go out and you put your hand out. And if you could do that, you would find that Jupiter's magnetosphere would be about 1.5 degrees. So that's bigger than the moon, bigger than the sun, which have the same size, so they can eclipse each other. And it would be quite a thing to behold. As it is, Jupiter's nice, and I hope everybody's been enjoying the view recently on clear nights. So what we're going to do in this talk, now that I've introduced Jupiter and its magnetosphere to some extent, is we're going to talk through the various regions. So we're going to talk through how we end up with this plasma torus and this plasma disk pervading the magnetosphere, how it leads to the generation of the aurora, what effect that has on the upper atmosphere, and then what we've been able to learn from Juno, which is flying just above the atmosphere in that neither here nor there region. So the first bit will be the generation of this plasma torus. So Io is the little moon that could, or perhaps the little moon that does, because it's still going on. Io is the most volcanically active body in the solar system. It's the innermost Galilean moon. So the most famous of those 80 moons are the 4 that Galileo saw from his spyglass. We have Io, Europa, Ganymede, and Callisto. Io, Europa, and Ganymede are in orbital resonance with each other, a 4-to-2-to-1 resonance. So for every 4 orbits that Io does, Europa does exactly 2, and Ganymede does exactly 1. What this means is that over time, those orbits have been slightly perturbed. So they're a little bit elliptical. And that means that the tidal forces along the orbit are different. So just like we have tides on Earth that are driven from the differential force of gravity across the body of Earth, the same thing happens here, except you're really flexing the body of the moon as it orbits through. This heats the interior, it removes water, and it drives volcanic activity. At Io, this leads to intense volcanism. You can see here, this is Pelon. In the top, on this side, if I can get this. So here is Pelon, and here's the crater 5 months apart. So there has been an eruption, some activity going on. Juno has recently imaged Io in the infrared, and you can see the hot spots all across the body of the moon. If you want to see what it looks like in action, we can even do that. This is a fantastic movie from New Horizons. And you can see the vast star plume up at the top going off. And I think this is amazing that we can see these geysers coming off the bodies of these moons. Now, for those of you who are excited about future missions, JUICE and Europa Clipper will be going to Europa and Ganymede, where it's perhaps not as much of an explosive effect, the tidal heating, but it does work to create subsurface oceans that are probably the prime candidates for life. And I don't dare to offend any Mars people in the room, but I say are much more exciting than a dry red planet that's in the local neighborhood. Okay, so Io is ejecting 1 ton per second into the Jovian system, and this is primarily sulfur dioxide in chemistry. This is neutral material that's coming out and filling out the local system. We can observe this from Earth. You can observe this from ground-based observatories, and it forms a neutral torus. So here are sodium atoms generated from that moon. You can see them around Jupiter, around the orbit around the orbit of Io. And then these are then ionized. And you'll end up with sulfur ions, oxygen ions, and different charge states. Now, the way that the neutrals are ionized is there's a variety of different processes. There is electron impact ionization. That's when a very energetic electron will come in, ionize it. There's some photoionization, although that's limited within the Jovian system. And the dominant mechanism of ionization is charge exchange. So that is when a rapidly rotating ion interacts with a slowly moving neutral, and they swap charges. So that doesn't generate any new mass to the system, but it will create a requirement for momentum. So what we're going to do now is we're going to talk about how this leads to the auroral mission at Jupiter. So sticking with Io, the Io interaction is going to generate an auroral signature. We have this moon. It is conducting. It is presenting an obstacle. There are ions in the environment. There's a plasma torus around it. And as Jupiter's magnetic field is swinging around with its 10-hour rotation period, because it's generated in the deep interior of the planet, it has to go past this moon, which is doing an orbit every 42 hours. That means that as the magnetic field swings past, it's going to have to drape over the field. You will have an alphanic interaction that results. Alphane waves, which are perturbations in the magnetic field, transverse waves that travel up, will travel along the magnetic field and generate a bright auroral emission that we refer to as the Io footprint or the Io spot. You can see this in the infrared. You can see this in the UV. There is also a tail of emission that is behind or upstream of the moon, downstream of the moon, and that's the dense plasma that needs to be accelerated and picked up to co-rotation with the planetary magnetic field from behind the moon. This involves a transfer of angular momentum. If you have a neutral molecule or a neutral atom that was going around at the Keplerian velocity of once every 42 hours, and it becomes ionized and it sees that magnetic field, it starts to gyrate around that magnetic field. It has to move with that magnetic field. And if you need to make up the difference to get your period accelerated from 42 hours to 10 hours, that needs a nice angular momentum kick. And this momentum can be transferred from these alphane waves and from electrical currents that will couple the two regions together. You also need to get rid of the mass. You can't be dumping 1,000 kilograms per second into a system forever. It eventually needs to leave. So you put this mass into the magnetosphere at Io's orbit, which is at 6 planetary radii, and it needs to move radially outwards. Now, the mechanism by which it moves radially outwards, I think we're still trying to figure out exactly what it is, but most commonly we invoke a centrifugally driven Rayleigh-Taylor-like instability. And this is a nice snapshot of 4 different times within an interchange instability simulation that Josh Wiggs, who's a grad student just writing up his thesis now at Lancaster, has been working on. And you can see that you have your heavy, dense material, and it's moving up into your simulation domain. It's going out this way radially through the magnetosphere, and being transported outwards. The plasma will be transported outwards, and once it gets past around 50, 60 RJ, and then spirals, does its final lap, and then is lost down tail. So it will move through the system, come down tail. In these regions here, you start to have a thinning. The plasma is wrapped into your magnetic field, but you're creating a very thin current disk, a very thin magnetic field perturbation. So maybe perturbation isn't the right word. If you have plasma, it's attached to your magnetic field, and you're used to a dipole, and then you're spinning it very fast, your dipole is going to start to extend. And that's the magnetic field structure that we see in the Jovian system. And as you move out through this, farther along, and you can see that structure here, these two parts of the field line will thin. They will eventually hit each other. You'll end up with a little bit of reconnection, and you can lose material down the tail that way. So that's how we're ridding mass of the system. But I'm going to go back into this region now within this red dashed line. So what is happening in here? If we look at the plasma angular velocity profiles from Galileo, so this is telling us distance is on the x-axis, and here the Galilean moons are marked out. So we're well within the magnetosphere. We're well inside that 60 to 90 RJ boundary. We're looking from 5 to 30 planetary radii. What these profiles are these are the angular velocity profiles of the plasma with radial distance in different local time sectors. So dawn of the magnetosphere, dusk, noon, and midnight. The dashed line on the top is co-rotation with the planet. So that's moving with a 10-hour period. This line is 80% and this line is 60%. If you were thinking of a typical angular momentum situation where neutral particles were moving out, as they moved out, they would slow down. What you notice here is that the plasma angular velocity isn't slowing down as it moves out with radius. Not really. So again, that's telling us that there's something coming. There's angular momentum being transported into the magnetospheric plasma, and that has to come from the planet. So here's a nice simple description here. Here you have your woman in a skirt on top of a rotating platform, and that's because if you're wearing trousers, it's hard to see the effect of the spin. So she's moving through, and this is effectively equivalent to what's going on in the Jovian system. So the plasma is moving outwards. It would slow down in the absence of the need for a interaction between charged particles and a magnetic field, but we have that need. And so what happens instead is as it moves out and tries to slow down, the magnetic field has to go with it, and that gets bent back. So you end up now with not only a thin, distended magnetic field, but it's a thin, distended, and swept back magnetic field. This curl in the magnetic field, or this bend in the magnetic field, has currents associated with it. And what those electrical currents do is they act to transport angular momentum to the plasma. They flow upwards out of the planet, along the magnetic field, radially outwards through the plasma, and then they will come back along a field line later, farther out in the magnetosphere, and close through the magnetosphere. In the region where they are radially outwards, there will be a J cross B force that acts to accelerate the plasma in the co-rotational direction. So to maintain co-rotation with the planet. At the atmosphere, there is a J cross B force in the opposite direction. So that's extracting angular momentum from the atmosphere and putting it into the plasma. Now, currents aren't aurora, but currents are the transport of plasma. And so you can get acceleration of currents and acceleration of particles into the atmosphere from this interaction. And that's exactly what we see. So I'm going to show you a couple movies now. This is a movie of Jupiter's aurora. This is from 2007. This is the Hubble campaign that was coincident with, I believe, the New Horizons flyby. So what you can see is you're at the Hubble vantage point, so Earth vantage point. And what you see here is you see the aurora rotating with the planetary rotation rate. It's not fixed in a central time frame. Sometimes you see it, sometimes you don't. You can see some other features on here as well. You can see the moons moving around. There was a moon that was just up or done, depends on what frame we're in. We'll wait, the moons will return. So here is Io, It appears to be retrograde, and that's because the planetary field is sweeping past it. So you'll see the Io spot, there's a Europa spot, and there's a Ganymede spot. So there are signatures of all of those interactions. Then there's this relatively constant omnipresent emission associated with the middle magnetosphere, and then there's the polar aurora, which I'm not going to get into in this talk just for the sake of time. If we were to take this now and put it into a fixed frame, so this is a frame now where you're looking down and you're rotating around with Jupiter, what you can see is that the location of that structure doesn't move. So the dipole tilt is around here. This is the Io spot, the tail and the footprint moving through the interaction. And this is that auroral emission associated with co-rotation enforcement that is mapping to the middle magnetosphere. This is completely different from Earth. If you saw movies of Earth, they would be fixed in the U movie frame, right? Or the Sun Earth frame. And if you looked at it and rotated with the planet, there would be a shift. This tells us it's an internal coupling that is driving this. So the aurora is the signature of coupling, and it's a signature of a huge amount of energy and angular momentum that are being transferred. The angular momentum is going out from the atmosphere into the surrounding plasma. And in return, we are depositing a lot of energy into the planetary atmosphere. And that input energy is about 10 to the 13 to 10 to the 14 watts. Now, if we want to know what that is in any sort of tangible quantity, that's the equivalent of 10,000 to 100,000 nuclear power plants. So this is a huge amount of energy that is associated with this interaction. And this is a lovely picture of the infrared emission that was taken from GRM that is on Juno. Okay, so now we're going to go on to what this has an effect, or what effect this has on the upper atmosphere. So we have to couple this aurora to the upper atmosphere. And when I say upper atmosphere here, I'm not talking about the clouds. I'm talking about the tenuous layer that you can't see above the clouds. So it's much higher up. And in that region, we're going to have an ionosphere. So we have our neutral atmosphere, and then we have charged particles, again, coincident with those neutrals. And it's a collisional regime there. So they are welcome to collide. And electrical currents will flow through this ionosphere. So here we have our current circuit again, except I'm focusing only on one hemisphere. And we have our currents flowing out of the planet radially outwards and back down and closing. And in here, you have your neutrals in the bright red, and your ionosphere is embedded within that. The collisions between the ions and the neutrals will generate a conductivity, and that conductivity will peak where the collision frequency of the ions and neutrals is equal to the gyro frequency of the ions around the magnetic field. Because there is a conductivity associated and there are currents, there are also electric fields in this ionosphere. And the frame that matters for electric fields, because for those of you who enjoyed frame transformation when you studied physics at some point, the frame that matters for this is the neutral winds. So we need to understand what the neutral winds are doing, how angular momentum is transferred within the planetary atmosphere to understand what exactly the magnetosphere sees. You can think of it as that upper atmosphere being a mask. You go to a masquerade ball, everybody is wearing some funny thing on their face. You have no idea who's behind. It's the same thing here. Whatever that mask is showing, that's what the magnetosphere sees, and that's what the magnetosphere can have access to. These currents will heat the atmosphere. They will alter the winds, and the processes that they do that by are Joule heating, which is a resistive heating, and ion drag. We can model these winds. So we can model them using general circulation models of the upper atmosphere. And the exciting thing here is that the vectors that are pointing are telling you whether you're having equatorward winds or poleward winds. And you end up with some shear flows. When we run these models, they map to the middle magnetosphere in the gray region, and we impose some boundary conditions on the outside. Now, the reason why I say we're modeling them is because we're very limited in what we can do for direct observations of these regions. You can use H3+, and you can use Doppler shifts in the H3+ measurements. And there are people that have done that extensively. Tom Stallard has worked on that quite a bit. And that will give you an indication of flows, but it's along the line of sight. And so we're kind of limited in what we can directly determine from the winds in this region. And so we have to get models involved. But at the end of the day, we need to figure out what the velocities are in the neutral atmosphere and what the velocities are in the ionosphere because that gives us an idea of what we can communicate to the magnetosphere. If we're extracting angular momentum out of the neutral upper atmosphere, somehow we need to get angular momentum from the deep interior back up. And this will happen through two processes. The first is vertical transport of angular momentum through eddy diffusion. And in that case, you have the deep interior rotating with the rotation rate of Jupiter. And as you move up, you end up with a rotation rate that is an atmospheric rotation rate, a midway point. And then as you go up higher, then you have a rotation rate that would be the magnetosphere. In this, you have a nice progression of your rotation periods that you can see. You can't take angular momentum out of something if it's moving more slowly than you, is the idea. Now, I think there's some interesting observations that will be coming out in the next year that might shake some of our thinking on this, that I've seen tantalizing glimpses of at conferences, but that's perhaps for another talk. The other way that you can transfer angular momentum is through meridional winds. So you can have winds that are going up from equatorward regions to poleward regions. And as they do that, because they're getting closer to the spin axis of the planet, they speed up. That means they're transporting angular momentum poleward, and you can have that process going. Now, the difficulty in these systems is you deposit a lot of energy into the auroral regions. How exactly do you get that to the rest of the planet? The same rapid rotation that's driving plasma out, and the centrifugal forces that are driving plasma out, are related to strong Coriolis forces in the atmosphere, and those Coriolis forces act to divert the auroral energy polewards. And this is a mechanism that has been reported in previous studies. And so this ends up leading to a bit of a conundrum. How exactly do you heat a planet? So there are a lot of ways that people suggest this can happen. One caveat of the models that have done this is that they've all been steady state models for the most part up till the last decade. So when we were saying there was this energy crisis, we were saying we have a nice spin aligned dipole, simplify the system because then you can start to back out characteristics. And we were ending up with energy confinement. And you can see that here, this is one of those simple models where our auroral energy has been transported to the poles. Now, this is the temperature that has been inferred from observations. Very, very hot in the polar regions, warm in the mid latitudes. One thing I want to point out here is the difference in scales. So this blue is 600 Kelvin on these upper images. It's 200 Kelvin on these images. So our strong Coriolis forces are confining the system. If you consider a nice steady state current system transferring angular momentum to our magnetosphere. And so we need to do something about that. Well, it turns out that you might be able to heat the equatorward regions if you have transient events. So if you consider changes in time in the system, so if you consider a solar wind compression, something that might move your magnetopause boundary inwards, shake things up a bit, push and exert on your outer boundary, spin up your magnetospheric plasma, enhance or modify the currents, that could lead to a leaking or an escape of energy to lower latitudes and heat the atmosphere. This was first predicted in models in 2012 by Jeff Yates, and he's done some further studies on that since. And we think there might have been some indication that this is what is happening in some H3+ observations that were reported in a paper last year. So there were two sets of observations, one from the 16th of April, which is the blue lines here, one from the 25th of January, which is the red line. And you see that the mid to low latitudes are warmer in the January observations. Now, these are a few days after there was a coronal mass ejection from the sun that's going to come through. That is going to put a lot of pressure outside, squish Jupiter's magnetosphere in, and alter the currents. So there might be a way that we can break this energy crisis and come to some sort of a partial resolution, at least, with energy from the outside of the planet being transported down in. Aside from that, there's also direct auroral energy deposition. So this is apart from the currents. This is just energetic particles coming in from the aurora, coming down into the atmosphere. They can excite the atmosphere, which would then de-excite and lead to the aurora, or they can ionize the atmosphere. Now, when they ionize the atmosphere, that has a twofold effect. It enhances coupling through increased conductivity, and then that will have knock-on effects for Joule heating and ion drag. So we're able to model this now with Juno, and this is really exciting. What we have here are some Juno UV images of the main auroral emission. We have a characteristic energy of these. So you can see that the energy of these emissions, the red is high energy, and then the blue is cooler energies. We can determine the precipitating energy flux of the incident particles. So we can do that as well. And you can get these UV false color images. And the nice thing about the UV false color images is they give you an idea of how deep into the atmosphere auroral electrons are going. The deeper they go, different species they ionize, and then that affects how much the conductivity can increase or decrease. And it also changes what layer of the upper atmosphere you're going to be coupling to and how much angular momentum you can extract. Okay, so I'm going to go into the in-between regions now and what we've been able to do with Juno. So just an introduction in case you're unfamiliar with Juno. Juno has been absolutely fantastic. It arrived at Jupiter in 2016. It's a highly elliptical polar orbiter, and it was designed to study the areas just above the atmosphere in many respects. As a perijove, 3,000 kilometers, so that's 0.05 RJ, that's really skimming the upper atmosphere. And an apogee, its farthest point is 113 RJ away. It measures particles and magnetic fields in situ. It has UV and infrared instruments. It has microwave instruments, and there's a whole bunch of other stuff it can do. But for the purposes of what I'm interested in, I'll focus on the particles, the magnetic field, and some UV and infrared observations. What has been really nice is when Juno arrived, it came in at dawn, so its apogee was at dawn, and its perijove was at dusk. It has now had enough time to swing around. It's entering a point where its apogee will be in the dusk sector, perijove will be at dawn, so we can start to disentangle local time effects, so things that are related to the day-night cycle at Jupiter with anything that's related to the planetary field structure and the rotation underneath. The orbit is also precessing with time, so when it started, this was the shape. Now it is dipping down, and we are starting to get into regions where we're skimming the polar atmosphere a bit more, whereas previously we were skimming the equatorial atmosphere. So this is going to be really great for people like Will in the audience who's interested in the X-ray emission that's largely in the polar cap. All right, so what happens exactly above the atmosphere? One of the big questions before Juno arrived at Jupiter was how exactly are particles being accelerated in? We had a lot of ideas, and they were informed by our auroral observations, and they were informed by expectations from the Earth system. The moons, I think we got mostly right. The idea was that at the moons, there was going to be alphanic, so broadband wave-driven acceleration of particles going into the atmosphere. And because we could see bouncing spots associated with the moon emission, there was clear evidence for what that was going to be ahead of Juno's arrival. For the main emission, for this middle magnetosphere mapping, there were a couple different ideas. And the leading one, I think, was that there was quasi-static acceleration. What that means is that there were fairly steady parallel electric fields sitting just above the atmosphere, that when the particles could get to that level from the magnetosphere in their current system, they would then be shot into the planetary atmosphere. This would produce a nice monoenergetic spectrum. They all saw the same electric field. They'd all end up in the atmosphere with the same energy. That was what was postulated, and it's not what we've ended up seeing, but I'll get there in a slide. And then there was speculation that the acceleration would largely be turbulence, broadband-driven acceleration in the middle magnetosphere. So Juno flies through, and I'm all excited because I think, yes, my thesis is going to be right. And then I became less excited because my thesis wasn't quite right. But the next thing to being right is to being referenceable. So as a theory that was there. So Juno really surprised us. Based on our lessons from Earth, we thought that above a fairly constant, steady auroral structure, you would see quasi-static electric fields. And that didn't happen. What you found, or what we found, what the data showed us, was that actually there's a lot more broadband acceleration going on than planned. There are some signatures of quasi-static acceleration, which you can see where the intensity of precipitating particles peaks and holds steady at a value. But there were also areas where that wasn't the case. You ended up with an infilling across all energies, and that's telling you that it's wave-driven. Perhaps even more interesting was that instead of having nice upward downward current structures, so upward currents would be associated with downward precipitating electrons, and downward currents would be correlated or related to downward precipitating protons. We found regions where there were bidirectional electrons. So our downward current regions still have electrons precipitating into the atmosphere, which we weren't expecting. And then we just saw far fewer electrostatic potentials than possible. Now, there have been a lot of studies showing this, and we sometimes see quasi-static structures. Sometimes we see a mix. Sometimes we have a spectrum where it looks like one's going into the other. With a single spacecraft, it's very difficult to figure out if it's a temporal effect or a spatial effect. And especially at Jupiter, where you're flying through perigeo so quickly that you're crossing quite a lot of magnetic field lines mapping to the middle magnetosphere, this is really difficult to disentangle. There have been statistical studies recently. The Salvatore et al. Paper is one of them. And what Annika did was she went through and she looked at the occurrence of broadband acceleration and the occurrence in quasi-static acceleration, and found that quasi-static structures, which we thought were going to happen most of the time, are happening less than 10% of the time. It is possible that as Jupiter's orbital trajectory changes and it gets lower down to the atmosphere, we might see a few more. If they're happening beneath the spacecraft, it's harder to detect them. But I've stopped holding my breath for now. It's good to breathe. All right. One of the other surprises was that there was more eogenic plasma at high latitudes than predicted. So if you have a rapidly rotating planet and you have a lot of heavy ions in that are coming from a moon, they are being spun quite quickly. They're moving at a 10-hour rotation period with the planetary field, or slightly longer if they're subcorotational. The thought was that those heavy ions would be confined to what we call the centrifugal equator. It sits between the rotational equator and the magnetic equator. They wouldn't be able to travel too far along the field because they were being spun. So you'd end up with your electrons being able to travel more readily along the field. And an ambipolar electric field would occur. And what an ambipolar electric field is it's a field that results from a charge separation. So that ambipolar electric field would act to pull electrons or negative ions down towards the centrifugal equator and try to pull up the heavy ions. This is a plasma density profile map from a Vlasov model that takes a magnetic field line from the EO flux tube and tries to model what the plasma density along that magnetic field would look like, what the electric potential structure along that magnetic field line would be. And in this region here, the blue region, there are no heavy ions. There is not any oxygen. Okay, so in this particular simulation that I ran, there was only oxygen, hydrogen, and electrons. So if there were sulfur up there, we'd be in trouble because I didn't include them. But the point is, there wasn't any there weren't any heavies getting up that high. This blue region here is the region that these plots are made from, and this is Juno data. What this Juno data is showing us is that there are a lot of heavy ions, so oxygen ions, sulfur ions, that are being observed just above Jupiter's atmosphere. And those are coming, they'll ultimately be coming from material from Io. So somehow heavy ions are being lifted up to high latitudes. Exactly why they're there, I think we need to better understand what's going into the system. The other thing that Juno's been able to do that we've never been able to do before is directly measure the field. Well, it directly measures the perturbation to the magnetic field above the atmosphere. And the nice thing about this is if you directly measure a magnetic field, you can then back out what the field aligned current structure is. So you can directly measure what the field aligned currents are. So we could have had a nice upward then downward structure that would map with a nice feeding angular momentum out to this plasma. It's moving as it's moving radially outwards, and then downward currents completing the circuit. Instead, what we're finding is a mix of upward and downward currents throughout. We also have found with Juno that there are strong hemispheric asymmetries, and this poses an interesting question. So the hemispheric asymmetries are maybe to be expected. The magnetic field is strongly non-dipolar. There's a magnetic anomaly in the northern hemisphere. The south is more typical, if you will. But how exactly those feed in to the magnetosphere, to the transfer of angular momentum, or even just to the types of acceleration that we're seeing, particularly in the northern hemisphere, remains to be seen. And then ionospheric outflow. So at Earth, there's a polar wind, so that's a pulling out of oxygen ions into the magnetosphere. And at Jupiter, there is an ionospheric wind that is H3 plus and H plus ions. Juno has observed H plus ions being pulled out of the upper atmosphere, heading towards the magnetosphere. And these are happening in the gap between aurora. So this is happening in between the EO footprint and the main auroral emission. There is some stuff there, but it's generally considered subaraural or fairly previously maybe uninteresting from a dynamical standpoint, although that's clearly not the case. So these ions are being pulled out, they're conjugate with the intertidal magnetosphere, and we need to understand what the mechanism is driving this. It's also interesting to know what the total mass rate or mass flux rather of protons going and H3 plus ions going into the magnetosphere will be. If you have more protons in the magnetospheric plasma, that could change the magnitude of ambipolar electric fields, say in the plasma confinement in the magnetosphere. So the big thing here is what exactly is driving subaraural ionospheric outflow. And Juno's given us some nice tools to quantify and test theories. All right, so I'm just going to wrap up with how do we advance our understanding in all of these things. So we have excellent auroral images. We have had those for a long time and they're improving. We have some fantastic in situ measurements. Galileo gave us tons of equatorial data. Juno is giving us all this polar data, and out near apogee, we're getting stuff out in the outer magnetosphere. And as its orbit tilts down, we're getting nice information in the middle magnetosphere. If we want to understand how to connect these things, how to connect our understanding of the atmosphere with our understanding of the magnetosphere, we're going to need to really spend a lot of time working on models in our field. That's the only way we can interpret multiple observations at the same time in a robust way and test physical mechanisms. So this is a non-exhaustive list, but this is kind of just a crib sheet, if you will, of various model types. So in the past and in the present, we've treated these in many different ways. The nice way is steady state. You can remove any time variation. You can run your model fairly quickly. You could say, I saw a lot of hot plasma in the magnetosphere, like Johnny Nichols has said, and then say, how does that change my auroral currents? And then map that with his auroral features. He's done some excellent work with that. You can take those steady state models and you can couple them to a general circulation model of an atmosphere. And then you can try and see how the winds are modified and changed. So that's something that quite a few people have done. And then and you can do a systems approach in MIT models as well. So MIT is magnetosphere, ionosphere, thermosphere. And that's, you take different data sets, try to back out the current, for example, from the different data sets, see if they match up. If they don't, that's telling you you're missing physics in one area. And there's a group in France, Michel Blanc's group is doing a lot of work on that. And there's been a nice paper by Al-Sayati recently that looks at that. You can focus on the alphanic interaction, and this is looking at the wave-driven acceleration and trying to see where is energy dissipated in the system, where are particles accelerated. And Joachim Sauer's group has done a lot of work in this along these lines for the middle magnetosphere, and there is quite a bit that's been done in the EO region as well. And you can run Vlasov models. So those are quite detailed, and they start looking at the plasma distribution functions, and you start looking at the pitch angles and the kinetic physics to see exactly how particles are accelerated. And that's nice because that gives you something to match up with your particle data that you're getting from Juno. And then you can do magnetohydrodynamic models, and these have an edge up in the time variability that can be captured in them. So you include quite a bit of physics. You evolve the system, you specify your boundary conditions, your plasma conditions, and you can really start to see structures. The caveat with those is that you often have to oversimplify the system, although you might say I've oversimplified it everywhere else, so why not there? But it just depends on what physics you're looking at. So you can't really get into the atmospheric end with the MHD models. But at the end of the day, what we need to do is we really need to improve our models, because it's the only way that we're going to be able to unite flows, precipitating electron energies, energy fluxes, ionospheric conductances, magnetic field perturbations, electric fields, neutral winds, auroral observations, and I'm sure there's at least a couple more things that I've forgotten. And if we don't do this, we're going to be kind of stuck saying, I think I have a case study of this event, and that's good enough. We don't want to be there. I think there's a lot of interesting science and understanding to be done. Jupiter's an archetype for exoplanets. There are plenty of hot Jupiters out there. I'm sure there are plenty of mid-temperatured Jupiters. And we really want to understand what's going on with those systems. There's a lot of work that's been done at Saturn, and I don't want to offend any of the Saturnian scientists in the audience. There could be many, many talks on that. I think one of the nice things that has come out of Cassini and the Saturn mission is Saturn, you really can see how much the atmosphere affects the magnetosphere and the periodic planetary oscillations and in other phenomenon. So just in closing, I hope that I've convinced you all that each region has a role. You can't really think of aurora and just say, oh, it's probably something in the magnetosphere, or think of a magnetospheric plasma angular velocity and say the atmosphere has nothing to do with it. You really need to think about both. If you don't consider the two regions or the three regions, depending on how you define the in-between together, I don't think you'll ever be able to fully understand the system. And if we don't have models, we're not going to really be able to interpret our observations and our in situ measurements. So numerical modeling is critical to developing any understanding of the system. I fully expect that we will be getting more surprises from Jupiter in the extended mission. And I look forward to seeing those. And thank you for your time.
Thank you very much indeed for a splendid talk, beautifully illustrated. Questions, please. Yeah, first.
Thank you, wonderful talk. Jupiter's main auroral ovals seem to be quite well defined and fairly constant. So what part of the magnetosphere do they couple to, and what is the source of such intense deposition in those main ovals?
So in terms of the radial range of the magnetosphere, so it's probably around 20 to 35 Jovian radii. So it's well within the middle magnetosphere. It's not near the edge, but that might vary depending on the local time sector. So it might be a little bit further out in the dawn region, a little bit closer in at dusk. And it will vary if there's a plasma injection event, say. So if there's a lot of plasma that's come in from the tail, that can distort the currents, that can adjust the emission. If there's a large event on EO, if there's a massive eruption, you end up introducing a lot more mass, that could bring the mapping of those auroral ovals in. And there has been one case where the oval has been seen to be coincident and sitting on top of Ganymede, which is at 15 RJ. So we can do a little bit with the moons and give us some information there, but actually understanding how to map auroral features out and doing that in a dynamic way is something that we really need to improve upon. Everything right now involves on statistical representations.
Thank you. Steve?
Again, very nice talk. Thanks, Lucia. So it's good you've got that cartoon of the magnetosphere up there, because what you can see is looking at the kind of a cut through noon to midnight, can't you, there? Those field lines loaded and the current sheet, as they swing round to the dawn side, they're going to have to contract back in again because they're going to have to fit inside the magnetosphere properly. And I just wonder if there are some acceleration mechanisms that can be throwing some of these heavy ions up to higher latitudes where Juno is now seeing them, because I agree that wasn't expected.
Yeah, so the local time of those observations, because we were from early in the mission, were dusk. So in order for them to be passing through, that would have been more dusk sector. And dusk sector has its own fun stuff, because as you move around from noon into dusk, you end up increasing the parallel energy of particles, and perhaps that's one of the explanations for that. So you do end up with signatures. You're quite right. As the tail whips around, and anything that's been stretched out has to then come within the confines of the magnetopause boundary through dawn. You will end up with acceleration of particles there, and you will end up with bright dawn storms that are associated sometimes with, actually, if you lose the plasma and it's lost down tail, and then you all of a sudden have an empty magnetic field line that's rushing in. that can bring some hot tenuous plasma back in with it. So I'm not sure if it'll explain those observations, but it's probably worth a look.
Thank you. I gather there's one online.
Thank you. This is from Emma Bunce, and she says, great talk this year, thank you. What future mission would you design to help understand this complex coupling scenario and test the next generation of models?
Multiple spacecraft. We need at least 4, preferably more. If there were a way to, I think okay, we'd really want something with electric fields, but that's just being greedy. That's not important. It's just greed. It's almost Christmas. That's what you're meant to do at Christmas, right? Sorry. But you would need at least 4 spacecraft to give some comprehensive coverage. And actually at Earth, we have it's 4 with Themis and 5 with MMS. Is that right? Because somebody's cringing somewhere if I've got that wrong. But Jupiter's a much bigger system. So you'd really want to have some way to have, maybe 16, because you could have 4 in each local time sector, and then maybe every now and then you could leave a local time sector alone and send some stuff. There is one other way though, and this is something that Will is one of Will's brainchildren, is the SMILE mission at Earth. If we could get something like that at Jupiter, that might be quite nice. If you could image the magnetopause boundary at least and kind of get some visual TV-like response. But still, 16 minimum.
Dear Santa, all right. How long, can I ask, how long is the Juno mission carrying on?
I think it goes through 2025 at the moment, the extended mission.
Another 3 years. Okay.
Is that right?
Question here?
Someone. That might be wrong. It might be another 18 months.
Thank you. A short question. Has Juno actually flown through any of the flux tubes from the moons? And if
so it's flown directly through a moon flux tube. I believe so, but I would need to double check. Will's nodding, so that's a good sign.
Okay. Next question. Any further questions? There's one here.
Has there been much thought about the historical evolution of Jupiter's magnetosphere? I realize that you're still trying to get the physics of the present magnetosphere, but has there been thoughts about how it would have evolved historically? And for instance, has the radiation environment changed to which the surfaces of, say, the Galilean satellites have been exposed to over time?
Okay, so let me answer the first part first. So in terms of, it depends on what you mean by historically. There have been studies that have looked at the evolution of the field over the last 5 decades using existing measurements and observations to say that there is a bit of a change. It might be driven by the deep interior. And I think that's the answer to that first question. Anything farther back, say, I mean, if you're talking about protoplanetary nebula, I mean, that it depends, or the dawn of the system, I'm not sure. In terms of how much it would change the moon environment, the moons, at least the ones I care about, are so far embedded within the system that I think you would need quite a big change, almost a turn on, turn off for it to have any effect.
Further question? Chris?
But I'd like to ask a simple dynamical question. This outward transfer of angular momentum through the magnetosphere, ultimately that's being driven by Jupiter's rotation. Do you have on that basis any estimate for the de-spinning time of the planet itself?
Not off the top of my head, but it was probably a good question for me to do for my 3rd-year students. It's negligible really, but.
The answer is that Jupiter is being slowed down, but in order to bring it to a halt will take several times the age of the universe as it is at the moment.
Sorry. Yes, I thought he was asking for an exact rate, Steve.
Oh, the exact rate. Oh,
yeah. But yeah.
Long. Any further? You?
First of all, the quote you gave at the beginning was Sandra Ticella for the.
Oh, neither here nor there.
For the universe is a beautiful place for the president.
Oh,
the other question, and this is not to be recommended, if one was still floating around in Jupiter,
Hmm.
what would the aurora look like?
Oh, it depends on where you were.
Yeah, so, you know, looking around, sort of seeing the footprint of Io.
Yeah, so actually, I have another talk. That I actually for local astronomical societies where I do this and I put some X's on and say, what do you think you'd see? So it depends on where you were floating. There are places on Jupiter that if you were floating, you would be always underneath auroral emission. But there are also areas where the EO spot would come passing over you every so often, and then places where you'd just be kind of bored and disappointed, much like on Earth. If you're in certain equatorial latitudes where you want to look up and you're just bored and disappointed. It also will depend on your southern or northern hemisphere because of the different magnetic configurations. And probably the most exciting place to be would be in the polar emission, where the aurora is so variable that you really wouldn't know what would happen at any given time.
Would better auroral observations help you much, or is it really the spacecraft?
The 16 spacecraft, please.
Okay. I was going to say, there's this space web thing that might look.
Yeah, James Webb is not, James Webb is lovely, Olivia. It's absolutely amazing and it's doing great stuff for Jupiter. I think we're going to be very sad when Hubble goes for the amount of information we get.
Good. Any further questions before we close? No? Well, thank you very much indeed for. May I remind everybody that there is a drinks reception held after this meeting in the RAS Council Room, just down the square, booze, in other words. And I give notice that the next ANG open meeting of the Society will be on Friday, the 9th of December, 2022. Thank you.